So welcome again, everyone. Thank you for joining us. It's a pleasure to have today Harshit Gupta, who was previously at EPFL and now at Stanford SLAC. Harshit is going to tell us about CryoGAN, which is a new approach to reconstruction, kind of an original perspective on how to do this. So I'm very excited about his talk. Harshit, the floor is yours.
Thanks, everyone. So I'll present CryoGAN, which is a new deep learning-based technique for Cryo-EM. And this work was mainly done at Biomedical Imaging Group at EPFL under Professor Michael sir. So first, I'll just discuss Cryo-EM, then the challenges that we have for Cryo-EM reconstruction, then the current methods which address those, and then our method CryoGAN, which is applicable for single conformation, its intuition algorithm, and some results that we have, and then its extension for the much more challenging problem for continuous conformation. So in Cryo-EM, as we all know, we take the identical copies of the same biomolecule and we freeze in the vitreous thin layer of ice, and we bombard it with straight parallel electron beams. And what we record is a micrograph, which has the 2D projection of these randomly oriented biomolecule. And our task is to reconstruct the 3D structure from these 2D projections. Now, the main challenges that we have is we get the micrograph and then we pick the particles. And by reconstruction, the main challenges are that for each projection, we don't know what is the conformation of the biomolecule because it can be changing the shape, it can be changing its conformation. We don't know from which orientation we took the projection because of the nature of the Cryo-EM. And we don't know the shift which happens during the picking of the particles. And there is a loss of information which is because of the optical effects of the microscope. And the other thing is there is high level of noise, which is because of low radiation dosage. So all these problems make Cryo-EM as one of the hardest problems in the field in terms of inverse problems. So the current methods, what they mostly try to do is they use a likelihood-based approach, where what they do is they have the measurement data set, which is projection of a biomolecule from different angles. And for each of these projections, they try to estimate the pose distribution, or they try to estimate the pose from which it came from. And this process is then iteratively refined to get better and better pose estimations. So what is done in the first step is to estimate pose for each projection, and then use this information to get the 3D reconstruction. And once we have the 3D structure, we can refine the poses back, and we can go back and forth and iteratively refine the process to get the 3D conformation. So most of the current software use this approach for single conformation. And for multiple conformation, we have many algorithms which try to estimate pose for each projection, as well as they try to estimate conformation for each projection. And because of this nature, they are mostly efficient for discrete when the particle is exhibiting discrete conformation. So now we are wondering if we can have an algorithm for which we don't need to estimate pose or conformation for each of the projections, so that the method can be less complicated. So for this, we propose CryoGAN. And the intuition behind CryoGAN is we want to reconstruct a structure whose set of projections from random angles or poses look similar to the acquired data. So what's going on is instead of focusing on each of the projection individually, we'll look at the whole group or whole set of the projection altogether. So we don't need to focus on each projection and estimate the poses. So the top bottom view of this method is based on GANs, where let's say you have a data set filled with facial images, and you want to have a method which can generate these kind of facial images. Now, for this, what we do is we use a adversarial technique where we have a discriminator, and the discriminator is trained to discriminate between real facial images and the fake facial images that we're going to generate. So discriminator, at some point, we give it the real data set. For example, here there's face of the Gaussian, which we give to discriminator, and it's a real face. And then we give it a fake face that we are able to generate, and we give it to discriminator. And we tell the discriminator that this is the real and this is the fake image. And then we have a generator, which is trying to generate these fake images, and it's trying to fool the discriminator in believing that what it is generating is actually the real images. So what happens at the end is the generator is able to, so what happens in the starting is discriminator is able to distinguish between the real and fake images, and it tells the generator what it can change in its generation so that the generated fake images look more like the real data. So generator is trying to generate more and more realistic facial images until the discriminator gets fooled in believing that the fake images look like real images. So at the end, the generator successfully generates images which looks like real data. And what it means is it captures the distribution of the real data set. So we take inspiration from this, and we propose similar algorithm for CryoGAN, which is basically we have the real projection data set, and what we are trying to do is fake this data set using our physics simulator of Cryo-EM. So the cryo physics simulator takes the 3D structure, which we are trying to estimate, and it gives us random projections from the simulator, which is actually modeling cryo physics. And the discriminator is being trained to see that the real projection which comes from a data set and this fake or the simulated projection that comes from our simulator looks similar. So the discriminator, and then we ask the discriminator what can be changed in the 3D structure so that its projections can look more and more like the real data. So in the end, the generator or the simulator is trying to create a 3D structure whose projections looks like the real data set, and the discriminator is trying to distinguish the two. So what happens at the end is, if everything goes fine, the simulator is able to find a 3D structure whose projections looks like the real data set, and that actually fools the discriminator. Now we'll go to the bottom top view of the method. So our method is actually hinges on the method called distribution matching, where you have the, let's say, the real ground truth, the actual biomolecule structure, and we have the distribution of the projections given this ground truth, and we represent it by a probability of y given x ground truth. And then we are trying to reconstruct a structure called xrec, and we are trying to reconstruct it in such a way that its distribution is given by py given xrec. Now what we are trying to do is, match these to distribution. We are trying to match the distribution coming from the measurements of x ground truth and the distribution coming from the reconstruction. We are trying to find a 3D structure whose distribution of the projection is actually equal to the data distribution. And the reason we are trying to do is because with some assumptions on forward model, we can prove that if the measurement distribution from two different structures are the same, then the two structure also the same, which basically means that if we can find a 3D structure whose projections look like the acquired data, then we can actually get the real ground truth. And this proof actually hinges on the a proof given by Panagiotis in 2009 using coupling theory. And the main crux of the proof actually is that we show that two different structures, if they have the same distribution of the measurements, then basically they have the same Fourier slices, but they're shuffled up. And we show that it's not possible to have this kind of situation because Fourier transform is analytic and have some common lines. So the bottom top view is there's measurement distribution or the acquired distribution from the real data. And we have the simulated distribution, which we simulate using our physics simulator. And what we are trying to do is find the 3D structure so that both the distribution match. So it's a distributional matching technique. So for this, we use the GAN, which we just discussed. And the nice thing about this is, since it's a set level of algorithm, not a individual projection algorithm, we don't need to estimate pose for each projection. It processes the data set at the data set level, not at each individual image level. So we don't require good initial volume, and the method is end-to-end. We don't need some other routine to give us feedback or some pose estimations. And just to reiterate back the thing, our method doesn't need any prior training or prior trained data set. So if we have data set coming from some routine, we just feed it to our method and we just get the reconstruction. So instead of thinking in the normal deep learning point of view, which is training, we can say that our method is actually optimizing. So we can say that our method optimizes or reconstructs the structure, because we are not exactly training. It's just an algorithm which reconstructs the structure, just like other algorithms. So now I'll focus on the algorithm. So in the bottom top view, we saw that distribution matching is a nice thing, and we can actually recover the ground truth using it mathematically. And now we are wondering what kind of distances we can use. So as we just discussed, we want to find the 3D structure X such that the distance between the distribution, the actual distribution probability Y given X ground truth, and our 3D and our distribution probability Y given X, their distance become minimal, which will represent as Pxy, Pxy given X. So we are trying to find the 3D structure so that the distance becomes minimal. Now we are wondering which kind of distances we can use. So we can go for the most small distance, which is scale divergence. And when you use scale divergence between the two distributions, what happens is you can simplify. And if you simplify scale divergence, what basically you get is, I mean, I can go through it, but I'll just give the simpler term, which is maximum likelihood, which is which is what most of the method use, which is maximum likelihood. So if you use scale divergence as the distribution matching technique, we get maximum likelihood. And the problem with maximum likelihood, as we discussed earlier, was that it is actually trying to maximize the log likelihood of each prediction given the 3D structure. So we are trying to find 3D structure which maximizes the probability of each of the prediction. And for this, we need to calculate probability of Y given X. We need to calculate conditional distribution of a projection given the 3D structure. And because of this, we need to marginalize or need to estimate the pose for each projection. And this is where the complicated task of pose distribution or pose distribution or pose estimation comes, which we want to skip. So then if we use scale divergence, we get the normal technique, which is maximum likelihood, and which we want to sidestep. Now we'll see also scale divergence is a convergence problem, which is if two distributions are really far from each other, then scale divergence is really degenerate, and it's degenerate until unless the two distribution have some common support. So you will never, if the two distributions are really far and have no common support, it's really hard to like minimize this problem because you won't get any ingredients to address your algorithm. Now we'll use a distance called Western distance. It has a very complicated formulation, which I won't go into. But if you see its dual form, it's a bit easier to see, which is we are trying to find a 3D structure which minimizes this expression. And this expression is basically, we are trying to find a function called S, and which we are trying to search in a space where it has some smoothness, which is less than 1 or equal to 1. So we are trying to find functions S in a very good family, and we are trying to find we are trying to maximize the formula where we sample the images coming from the actual data and we feed it to this function S, and then we sample the functions from our similarity distribution and we give it to this function S, and if we take the difference between the two, it's maximized. So we're trying to find a 3D structure such that this function, which maximizes this distance, is actually minimal. So it's actually a bit hard, but yeah, like it's a bit less intuitive, but like this is what the distance is. So the nice thing about this distance is we don't need to calculate probability of Y given X, which was needed for scale divergence. And if you can see the formula, we just need to sample from this distribution. So if we use scale divergence, we get maximum likelihood, where we need to calculate conditional distribution of each prediction. But if we use Western distance, we just need to sample from it. We don't need to calculate it. And this is where we get, we sidestep the pose estimation. So another nice thing about Western distance is it has some good convergence. So if two distributions are really far and they don't have any common support, it is still generate, it is not degenerate, it gives some value, meaningful value. And the closer you bring it in intuitive sense, the lower the Western distance is. So which means it can give us meaningful gradient so that our method can rely on it. So just understanding what we are trying to do is we have the Western distance in the primal form, which has a dual form of using another function, external function S, and this helps us to calculate the value of Western distance. And in our method, what we do is for these function S, we try to approximate them using universal approximation property. And we use a function called which we represent using an input called discriminator. So a discriminator has some parameters phi, which we can change so that we can span this space of eligible functions. And we are trying to find a discriminator so that it gives high value to the data distributions, which is coming from the acquired measurements, and it gives low value to the simulated measurement, which comes from the simulated distribution. And we are trying to find a 3D structure which minimizes the distance between these two formula for all the discriminators. So we have we are solving a min-max problem. We are trying to modify the discriminator so that it becomes higher for data distribution and lower for simulated measurement. And we are trying to modify the 3D structure so that the discriminator can't have this, so that the gap between these two calculations is minimal. So just to clear what we just discussed, we are trying to match the distribution that will matching the distribution, or the distribution matching technique can give us the ground truth. And if we use scale divergence for distribution matching, we'll get the maximum likelihood techniques, but it needs to calculate probability of y given x, which needs marginalization of pole distribution routines. Whereas if we use Western distance, we don't need to calculate this likelihood value, and we just need a sampler. And we use a neural network called discriminator to calculate this Western distance. And in normal GANs, there's Jensen-Stein divergence, which is used, which has similar property. So now, as we discussed, Western distance doesn't need any log likelihood calculation, but it needs a sampler. So our task now is to build this sampler. So this sampler is basically our simulator or generator, so which basically relies on the cryo physics. So if you have the 3D structure, we can sample by sampling a random rotation from some distribution. We rotate the 3D structure, we take the 2D projection of it, then we shift it randomly by some t, which comes from some distribution. Then we convolve it with some CTF whose parameters comes from some distribution, and then we add noise to it, which again comes from some distribution. So basically, when we sample these latent variables or hidden variables, we basically get sample from the actual data distribution that we from the simulated distribution. So sampling from this distribution is basically sampling these latent variables, doing the cryo physics, and getting the 2D projection. So in this way, we can get the sampler, and this is the fundamental part of our algorithm, because we just need a sampler to calculate our Western distance, which we are trying to minimize. So nice thing about this, about having this kind of simulator is it's backpropagable. So as we will see that in order to get the 3D structure, we need to change some values in it. And we give these samples to discriminator, and the discriminator tells what it wants to change. And we need to backpropagate or send this gradient back to the 3D structure. And all these forward passes that we just discussed are actually backpropagable. So if you want to change this region in the 2D projection, this can be backpropagated, and you can see what you want to change in the 3D structure. So I'll just discuss the whole CryoGAN algorithm. So we have the real pick particles, we sample projections from it, and we give it to a discriminator, and we train the discriminator. We change the value of the discriminator parameter such that it gives high value to these projections. At the same time, we have the physics simulator, which takes the 3D structure, which can be changed, and we simulate these 2D projection, and we give it to discriminator, and we tell the discriminator to output low value for it. So the discriminator learns to give high value to real particles and low value to fake particles. And at the same time, we change our 3D structure such that it gives in such a way that the change structure will give high value to the high value through the discriminator. So basically, we change the 3D structure such that, and this information comes from within the discriminator, such that we can change the 3D structure such that this fake image can fool the discriminator a bit more. So the discriminator will give high value for these fake images. So, and we just iterate back and forth. We train the discriminator to give high value to real data, low value to fake data. And in adversarially, we train the 3D structure so that it creates prediction which gets high value through discriminator. And when we play this min-max game, we hopefully converge to a point where the fake predictions from this simulator looks like the real data, and the discriminator can't really distinguish the two. So now I'll discuss some experiments and results. So we created a synthetic experiment where the level of noise was minus 20 dB, which was similar to the real world scenario. We used synthetic beta galactoid volume, and we fitted an atomic model of 2.5 angstrom on it. And sorry, we created a density map from the atomic model at 2.5 angstrom. And we took 41,000 projections of it using uniform distribution of the angles. And we took realistic CTM noise conditions. And the noise that we added was extracted from the experimental micrograph of the same protein. So we have 1,000 projection, and we feed it to the CryoGAN algorithm. And we can see that in 10 minutes, it gives an ab initio kind of reconstruction, which is 29 angstrom. And after 400 minutes, it converges to something like 8.6 angstrom, with the ground truth had like 2.5 angstrom of information. So if you see the trajectory of the prediction that the CryoGAN is trying to create, you can see in 10 minutes, it somehow gives some predictions which look like the real predictions, the real clean predictions, but like the high frequencies are missing. And as you go in the time, it fills in more high and high frequencies, and so that the predictions look much more like the real data, so as to fool the discriminator. So if you see that the final clean prediction before we add the noise or corruptive CTF looks like the first row, then we add CTF to it as our simulator has, and then the final simulated images in the third row, and the fourth row has the real data. So real data. So basically the last two row is what the discriminator sees, and our method converges when the discriminator can't distinguish the two last rows. Then we run a method on experimental data for the same protein, for similar condition from MPR, and we estimate for this method, for this data, we estimate the CTF, and we assume uniform distribution of in the generator or sampler, and the noise that we added to our simulator was picked from the micrograph background. And what we see is in 150 minutes is something like 12 angstrom, an ab initio kind of reconstruction. And you can see like it fills in higher frequency information with time. So now I'll discuss extension of CryoGAN for continuous conformations, which is actually an open challenge in the field to reconsider the continuous conformation of biomolecules from Cryo-EM. So as we all know, that structural heterogeneity is key to understand the biological functions. For example, this is a shock protein, and if we can get the understanding of its biological mechanism on conformations, we can understand that its functions, and it's an open challenge in the field. So we extend CryoGAN to MultiCryoGAN in a similar fashion. So instead of likelihood-based method for which we'll have to estimate poses for each prediction and conformation as well conformation in this case, we try to sidestep both of those steps. So we have the measurement distribution coming from the real data, and we're trying to find we are trying to create a similar distribution whose distribution, and we are trying to find 3D conformations so that this distribution matches the real distribution. And in our case, the way we are generating the simulated distribution is using a 3D neural network called a generator. So a generator is fed with the latent distribution or latent variables, which try to control which conformation we generate. So we feed in some latent variable to this 3D generator. It gives us the 3D conformation or the 3D conformation volume, and we use our physics simulator to get the projection. So basically, we are trying to simulate cryo physics when the structure of the molecule is changing. And we are trying to find a generator or a way to get the 3D conformation distribution whose projections look like the real data. So just like CryoGAN, we don't need to estimate pose or conformation, and this method can recover both discrete or continuous conformation manifolds. And similar to CryoGAN, we have the guarantee of recovery of the true conformation, and the proof is quite similar to CryoGAN. So in essence, we again have a discriminator, which is trying to distinguish between the real and fake data. And this fake data is now coming from a bit more complicated process, but not that hard to understand. So we have a 3D network, which takes a latent variable and gives you the 3D structure, which we feed to the physics simulator, and we get the projection. So we are trying to learn, we are trying to find this 3D neural network so that the low dimensional manifold of the conformation that it generates fools the discriminator. So this can be actually seen as a WGAN structure or Western GAN structure with a physics simulator in the generator. And the generator is actually transforming the latent distribution into conformation distribution. And the cryo physics take this conformation distribution and makes it in the projection distribution, which gives to discriminator. And the discriminator is trying to match it. And we are trying to change the generator so that the two distribution match. So we ran our data, we ran our method to the data on a simulated data set where we had two data sets. One was continuous conformation, and another had discrete conformation, and the predictions look something like this. And for each of the case, we took 100,000 predictions, and we used some CTA modulation, and we added Gaussian noise minus 10 dB. And in the simulator, we assumed that the latent distribution is actually uniform on a 1D line. So this is the reconstruction we get. So this is the ground truth, the 3D structure from which we simulated the data. And you can see that the bond angle of the heat shock protein changing from 0 degree to 20 degrees. And here's the reconstruction, which is basically, so reconstruction gives us the neural network, 3D neural network. And what you see here in the right side is we traverse on the latent variables and we get these 3D conformation maps. So as you can see that the reconstruction is our MultiCryoGAN can faithfully reconstruct the conformation dynamics of the actual ground truth. And if you look closely, the ground truth is going from 0 to 20 degree, the bond angle. And the reconstruction that we get, as I just said, we go from one latent variable to another latent variable on a single line. And as you move on this line, you can see that the bond angle goes from 0 to 20 degrees. So basically, not only we can get the dynamics, but we can also reconstruct or get the hold of the actual factor of variations or the actual degree of freedoms. And here in the bottom, you can see that the real clean projection and the fake clean projections, and the real projection and the fake projection that we give to the discriminator, and for which the discriminator gets food. And we repeated the reconstruction on the discrete conformation data set where we had two types of conformation. One was 0 degree bond angle and 20 degree bond angle. And our reconstruction gives a latent space in which 25% of the latent space maps to the first conformation, which has 0 degree bond angle, and 70% maps to 20 degree bond angle, which had 75% probability. And the 5% in between is utilized to smoothly transition between those two. So this proves that not only we can reconstruct continuous conformation, but also discrete conformations. So I'll just again reiterate what we discussed about CryoGAN versus likelihood methods. So normal methods use maximum likelihood method, the current techniques, and they rely on a thing called K divergence, which is a way to minimize the distance between the real distribution and the distribution that distribution of the measurement from the reconstruction. And once you do that, you need to calculate the conditional distribution for each projection, which needs to estimate the poses for each projection. And instead of K divergence, if you use Western distance, because of the form of the Western distance, you just require a sampler from the distribution. You don't need to calculate probability of y given x. And as we discussed, sampling from the distribution is basically emulating the cryo physics, which is actually similar to cryo physics simulator. So theoretically, both are same. Both are distribution matching techniques, but one is explicit and one is implicit. In conclusion, we propose a deep adversarial learning scheme, and this does not require any likelihood computation or pose and conformation estimation or marginalization. And it's first self-sufficient deep learning based method which can reconstruct continuous conformations and doesn't need any external pose estimator or external routine. And it can theoretically recover the ground truth. And it's similar to GAN, but with a physics-based generator instead of neural network-based generator. It relies on distributional matching paradigm, as we discussed. And for single conformation, it works reasonably on Sunday experiments. And for multiple conformation, it still needs to be deployed in real data. And just like GANs, where the phase transition happened with multi-resolution approach like style GANs or progressive GANs, where at one point they were not able to generate facial data set and they were really blurry. Then to the current status of GANs, where they can generate faces which looks really like the real faces, and this came from multi-resolution. So we hope that using some multi-resolution approach or technique on those lines can help us get 3D reconstruction whose predictions look really like the real data, and which can actually help us with the resolution. So these are the references, and yeah.